Hello, welcome back. So now in this video we are going to see beams analysis, how to do the beams analysis in Ansys. Till now we have completed bar, trusses. Now we are moving to the structural problem. This is also called as 1D bar problem, 1D type of problem, that is beams. So beams is also a structural member, one which will carry the transverse load. So the application of this is beams we are going to use in all construction of buildings as well as in bridges, and we are going to use. There are different types of beams will be there, like cantilever beam, simply supported beam, overhanging beam, fixed beams, and continuous beam. So out of these, for a syllabus we are going to take up cantilever beams, simply supported beams problem. Along with that, there are different load conditions will comes, that is like point load, uniformly distributed load, and uniformly varying load. So now with respect to that, we are going to deal with them one by one. So the first problem is, that is cantilever beam problem. So the beam, you can see in the figure, the beam substitute a concentrated load for the beam shown in figure. So find the deflection as well as reactions. Take E is equal to 210 GPa as well as I. So I is nothing but moment of inertia into 10 raised to minus 4 meter per 4, and they are mentioned clearly. You have to take two elements. So this is a figure. Now cantilever beam is one side is fixed and other side is free. Now this beam is subject to a constant load of 5 kiloton. So up to here it is 2 meter, and here. Now here the property, till now we have seen in the bar and the trusses, they are given the area as well as Young's modulus. But now here Young's modulus as well as one more thing additional to that, real constant I value they are given, that is nothing but moment of inertia, that is 2 into 10 raised to minus 4 meter per 4. Now we need to find the what is a deflection as well as reactions. So everything we given given in a meter, so even answers also in meter only, therefore will let me do it in meter itself. So let's proceed into the Ansys window. Now let me go to first preference, structural, okay, then preprocessor, element type, add. Now this is one more very important step. So till now we have selecting for power and trusses link. Now for this we have to select beam, that is 2D elastic 3. Press OK. So therefore with respect to this we are going to assign the real constant. Now you can see the real constant for a link, it is asking only area. Now it is asking area, moment of inertia, height, as well as these three. Now with respect to beam problem, we need to mention the area, we need to give a moment of inertia as well as height. So area is not given. If not given, take it as unit area, that is 1 mm square or 1 meter square, and I Z. I Z is nothing but moment of inertia, that is 2 into 10 raised to minus 4 e power minus 4. And what is height of the beam? That also not given. So if they given the cross section, they are going to mention. Now if they are not given means assume as unit height, that is 1 meter. So therefore real constant part is over. Now we need to create a material models. So here material models, there is no changes as usual, structural, linear, and elastic. We need to assign a input of Young's models as well as Poisson's ratio. So Young's models is 210 GPa, that is 210 e power 3, and this is 0.3. Press OK. Now let me close this. Now we need to modeling, we need to do, for that we need to create nodes. So let me check before going to that node, how many node we need to divide into 3 minutes. So 2 elements means 3 nodes. Here node 1, here at the middle at the load acting point node 2, and here 3. Say for node 1 is 0, 0, 0, node 2 is 2 comma 0 0, as well as node 3 is 4 comma 0 0. So let me give the same coordinate system here. 1 is 0 0, apply. 2 is 2, apply, and 3 is 4. Press OK. Now we need to give element auto number through nodes 1 to 2, press apply, then 2 to 3, press OK. So we complete the modeling part. Now we are moving to the important thing, boundary conditions. So in boundary conditions, we need to give fixed at this node 1, that is all degree of freedom, and also at node 2 we need to apply a concentrated load downward direction. So let me give the same thing in the solution. Go to define and define loads, apply, as well as structural displacement on nodes. So let me fix on the node 1 in all directions. So we are fixed means it is in all direction. We need to apply a nodes, that is at node 2 in down F5 direction, that is downward, that is minus how much, 5. Therefore minus 5 kilonewton only we are going to take. This completed the pre-processing part. Let me take up to the solve. Okay, solution is done. Let me go to the general post processor. First is reaction solution wins. So list results, reaction solution, and press OK. See this now. So which node we fixed? Node 1. Therefore reaction will produce on the node 1 only, where node 2 and 3 there is no thing. Therefore at node 1 only, so 5000 is there. So because we applied 5000 constant load, therefore minus 5000, and this is plus 5000. And also because of this load, what will happen? There is a bending moment taking place. So what is bending moment? Force into perpendicular distance. Okay, so now with respect to this 5 into 2, that is how much? 10. So same 10 Newton mz. So mz is nothing but movement in z direction. Always keep this in mind. Bending moment nothing but rotation in z direction. So therefore we'll verify with the answer here. Reaction at node 1 5, as well as node 1 it is 10. This is 5 kiloton, and always bending moment is force into perpendicular distance. Therefore it is in Newton meter or Newton mm. We are given here kilonewton, therefore it is kilonewton meter. So we got the same answer. And in question they are also asking deflections. So let me see the deflection now. For that, first we'll see the graphical presentation. Plot results, contour plot, nodal solution, that is TOF vector sum. We'll take it. Now we can check 0.79 maximum is there. To view in a table format, that for that list results and nodal solution. So let me give in vector sum. Okay, so instead of that, if you okay, so nodal solution, if you give the deflection, so which direction deflection is taking place? See, the rotation take place, bending will take place in z direction, whereas this is going to deflect in y direction. So let me give the y direction, then press OK. Now see this, node 1 is 0, node 2 is minus 0.31, same, right? And this one, this is 0.793, so this is 0.793. Okay, now let me check the one more deflection. So this is linear deflection. Now there is a bending moment, no, that is also kind of rotation deflection. So therefore that is going to take place in a y direction, right? So therefore let me view in the z component. Now you can check node 2 and node 3, what is the combination. This is in radian because rotation taking place, that is we are going to measure in terms of radian. So we got the same answers, and you can check 2.3 into 81 into 10 raised to minus 4, that is nothing. We got in 0.23 radian. Okay, then one more thing, we are going to represent through the graphical representation list results, plot results, nodal solution. You can give vector sum 0.73. So that is, where is the 0.73? At node 3. And if you want to see the stress, give the stress value here, and you can give yes, that is not visible. So for this, so I think in the question they are not asking the stress. Now if addition to this, suppose in cases other problems they are asking the bending moment and shear force diagram as well as stresses also. So let me do this problem only. Okay, so for this we need to create a element table. So for that element table, the thing is very important. So we need to, you can check out here, for BMD we need to create a table like two combination. So we are taking for two combinations for I node and J node, that is BMD, and that by sequence number SMIC 6 and 12. For SFD diagram, SMIC 2 and 8 combination. For stresses 3 and 6. So that is, let me see, BMD I node come down by sequence number and SMIC comma 3, right? 6 comma 6, press apply. Again BMD for J node, this is just for our reference. Okay, by 6 SMIC comma 6 comma 12, apply. Now for SFD for I node, again same by sequence number SMIC comma 3 not 3, 2 comma 8. So first 2 for I node, and for J node we need to give 2 comma 8, means SMIC comma 8. And also they are asking, suppose if they ask stress, in the next problem the same questions will come. Now we are going to do for this problem only stress, that is bending stress. So stress for I node by sequence number, here very important thing is we need to select a LS. So LS combination is 3 comma 6. Therefore we are going to 6, apply. Then we are going to take up the sequence number LS comma 6 comma 3 comma 6. I think this I'm going to delete. Okay, I'll have to add one thing. So stress for I node we need to give 3, LS 3, apply. And for stress for J node in sequence LS comma, what is one more number, we need to give 6. So therefore you can see there are 3 table grade. BMD, these are 2 combination 6 comma 12, SFD diagram 2 comma 8 and 3 comma 6 for stress. To view this result we need to see here plot results, element table, line element table, select SMDI, SMDJ, press OK. Now this is the bending moment diagram. The maximum bending moment taking place here is minus 10 Newton mm meter. For estimate for to view this shear force diagram, so for I node SFDI, for J node SFDJ, press OK. That is 2 kilonewton. So keep this in mind, shear force in kilonewton or newton will be there. PMD either newton meter or kilonewton meter, newton mm will be there. Now to view the stress for I node, stress I, J node, stress. So anyway, this also we got maximum. So that is here maximum will be there, that is minus 25,000. So but it's showing minimum, right? Why? Because blue column is because negative direction, more than negative value it is minimum, but this is only the maximum. So this question is they're not given, I asked it, but addition to this problem I just explained here itself, in the next upcoming problem also they are going to ask the compulsory, so most of the cases shear force diagram as well as stresses. I hope you are understood. uh, we'll proceed to the next problem next. Thank you.